All right, so today we're going to start what we call machine learning. We've looked at how to do basic implementation with Python. We've looked at how to load your data into the IDE you choose, which in our case, we're actually choosing, we use the Jupyter Notebook as the IDE that we're actually using. And then, so we've seen how to load your data into your IDE. We've seen how to manipulate those data, how to deal with missing values. We explored different areas on how to undo missing values. We looked at how to maybe use the feed forward method, the backward fill method, the fill forward, the backward fill, how to fill the missing values with its average and things like that. So we've looked at all of those different areas on how to use to fill the missing values and all of that. So, and then we've looked at data visualization using matplotlib and Seaborn. So we looked at how to create scalar plots, how to create bar plots, how to create even using to create density plot using Seaborn, histogram, and all of that. So now that we've been able to visualize our data, we've been able to manipulate our data and also visualize it. Suppose the end goal is to build a predictive model. How do we go about that? And that's what leads us to what we call machine learning. So machine learning, a lot of people, misunderstood that word. What do we mean by machine learning? I know some of us must have heard of it. What do you think? What comes to your mind when you hear the word machine learning? Anybody?
I think it's trying to tell the machine, maybe you have a data, and then try to tell the machine to use that data to make a prediction for you to compare it with what you have already.
Okay, that's right. You're not wrong. That's right. Any other person, Mr. Emmanuel, Mr. Bolaji, any idea?
Good afternoon, sir.
Good afternoon, sir.
Sir, I think machine learning has got to do with telling the machine, to make out a sense out of the data, and based on that, you should come up with a model that will enable us to make prediction, when we get future values and all that.
Okay, you're correct. Also, so
I also think that machine learning is also to identify patterns and also to make decisions in a minimal human intervention. So, which means that machine will be the one making the decisions, while we have the minimal control over the machine.
That's right. So it seems you all you all have an idea of what machine learning means. So you're all making reference to something, data. So that means machine learning thrives with data. And we've talked about data. We said data, in this our case, we're talking of structured data, but it could be unstructured like text, images, but we're talking of structured data in tables, in rows and columns. So we're all mentioning data, and then we're all mentioning that we want the machine, we're giving machine an instruction on how to use the data to make sense out of it. So that is basically machine learning, what machine learning is about. In the past, programmers used to give rules, like design rules for this machine on how to make sense of the data, on how to use the data to make prediction. However, we saw in the past that rules, they are not scalable, meaning that they are not perfect, they are very susceptible to errors because the rules are so many. It's just like you want to give a rule to a machine to detect whether this particular incidence is cancer or not. So that means you may have to code do that. Maybe if the body weight, the body mass index, the body weight is this, if the person is on eating this particular diet, if the person is smoking. So you have to design all of those. And there are so many. So we realize that has a great limitation. And then the rules are so many that they are just not scalable. And that's what makes machine learning to now, okay, instead of designing rules, can we allow this machine can we just supply data to this machine and allow the machine to use the data to learn, to try to find a function or a pattern in this data and come up with a model. That model means come up with a rule by yourself. So that model, when we say a model, we mean come up with a function, come up with a rule. Instead of we giving you rule, we just give you data. And you use that data to come up with a rule to say that, oh, if this person has this, that means this person has cancer. If this person does not have this, that means this person doesn't have a cancer. Or we just, maybe from that rule you say, oh, if the price of this house, so if I see a data that has maybe the population of that area is this, the income level of the people in that area is this, then the housing price should be this. So the machine is the one coming up with those rules rather than you. And that's what we call machine. So instead of man, like Mr. Bolaji said, be the one to make that rules. Let's make the machine to come up with that rule. But we'll say, what do you mean by machine here? So the machine we're referring to here means algorithms, but we'll see the several ones. Okay, so we've laid the foundation for machine learning. So we said it's actually a act of enabling machine to learn from experience. By experience, we mean from data, without being explicitly programmed, without being explicitly designing rules for this machine, for these algorithms. So I put other things there like the AI, artificial intelligence, and deep learning, but my focus is on machine learning here because they are all interconnected. Okay, machine learning is a subset of AI and deep learning is a subset of machine learning, but let's focus on machine learning. So like we said, it's a subset of AI. It uses statistical methods, to enable machine to learn from experience, to improve from experience. By experience, remember, we mean data. Okay? Feel free to stop me if you have a question. Now, let's look at the different types of machine learning. So by the time we talk about machine learning, we have two types, or we have basically three types. We have the supervised learning. You can see it in this red stuff. We have the unsupervised learning. You see it just at the left here. And we have the type that is called reinforcement learning. And that's the type that deals with the robotics, designing games for this AI, designing games and all of that. By supervised, which is the aspect we're going to focus on for this class, supervised is further divided into two. So remember, we have supervised learning and unsupervised learning. What do we mean by supervised learning? I'll go into that. By supervised, we mean we kind of have an hypothetical teacher, something guiding the building of the model, something guiding our machine, our computer, on how to design the rules. Remember, we said machine learning is about the machine designing rules, or coming up with patterns, looking for patterns in the data. Now, how the machine we make the prediction, we come up with a function, or we look for patterns. How to do that is what leads to whether supervised or unsupervised. So if the machine has support from an hypothetical teacher, remember, you remind me, hypothetical means you can't physically see the teacher, but if the machine has a guide, a kind of a teacher teaching it on how to come up with those rules, how to make that prediction, then we say it's supervised, meaning the machine is being taught how to do that. What do you mean by being taught? Meaning that in the data we are supplying to the machine, There is a column which serves as an example of what we want the machine to predict. We call that column the target column or the output column. So it's actually an example of what we want the machine to predict. So that column, the target column, which is the hypothetical teacher, will be teaching, guiding the machine on how to come up with those rules or how to look for the pattern or how to make that prediction. Are you with me?
Yeah.
Yeah.
Am I too fast?
No.
Okay, good. So that's what makes it supervised. Now, if you supply data to the machine and it doesn't have that target column or the output, something to teach it, then we call that unsupervised. So we say here, so we are saying here that for supervised, there is something, this machine has something like a teacher. So for this, we have a teacher, something to teach it. So the machine is being taught. Okay, that's what makes it supervised. But here, the supervised doesn't have teacher, no teacher. Okay, so that's what makes it unsupervised. Now we can further develop the supervised into two. The supervised can be further divided into two. So we have what we called the classification and we have the regression. So we have the classification here and then we have the regression here. By regression, and you will see as we move on, and that's the aspect we're going to stop today. Regression here means our goal of the model we want to build is to predict a numeric outcome, like the housing price. Like you see here, we have weather forecasting, market forecasting. You want to build a model to estimate life expectancy, just like we have in the Titanic data. Or you want to build a model to predict advertising popularity, how popular the marketing campaign is. So those are numeric values. If the end goal is to build a model to predict numeric outcome, then we call that kind of a problem regression problem. Okay, but if the outcome of the model is to build something called a model to build whether a customer is retained, to build whether a customer will leave or not, we call that kind of a model, we call that classification. We call that classification. So in that case, we say that is like customer will leave or not, diagnostic or not, cancer or not, things like that. Those ones, because you have categories, yes or no, fraud is detected or not. So we call that classification. So you want to build a model to predict the categories of a particular category. Okay? Any question on that?
None from my side. None from my side.
Okay. All right. So that's the ideal of machine learning. So for our class, we're going to focus mainly on the supervised and on the unsupervised. And today we'll focus more on regression. I need to establish these theories, this understanding of the background before we go into coding, so you will understand why you are doing what you're doing. Okay? All right. I need to clean up this. Okay. So let's look at some machine learning terminologies. You will hear about most of these out there. So for machine learning, you want to talk about training data, because you are dealing with data. But we don't just feed all this data to the machine at the time. There is a reason. The end goal of building a model is that because you have a data, the end goal is not basically on the data you have that you use to build the model. The end goal of building a model for a business is that they will use that model to predict on a new data, separate data that you did not use to build it. They will use it to make future prediction. So in that case, you want to simulate the experience. You want to have an understanding of how this model I'm building using this data will behave if I supply it with a separate, new and fresh data that it has not seen before. So because of that, when you want to build the model, you need to simulate that experience. So that leads us to break the data, to split the data into, most times some people use two, just the training data and test data. But in the real world, there is better to split it into 3. I'm going to start coding with splitting 2, but I will show you before, I will also show you later how just breaking them into 3 parts. So the training data is the data that we basically use to build the model. The validation data is the one that we use to check how the model is performing and to tune it, to adjust some of the parameters so as to squeeze out the best accuracy. And after you are fully satisfied with your model that, okay, this model can go into production, meaning I am ready to deliver this model to the customer, it is now perfect or nearly perfect, then I can finally test it, validate the model with the testing data. Any question at this point on data, training, the validation, and testing? Any question? Are we good?
None from my side.
Awesome. Okay, so before let me show you and then after this slide, we're going to go to our Jupyter notebook to see how to do some of the things I've talked about. So this is a summary of a model life cycle. Okay, the model is about training. Okay, and machine learning is just all about using data to build a model to make prediction on future data. So it all starts with data. And then we split the data. Remember I said most times, most people use just 2. So let's say you only want to use the training and testing. So you split the data into a training data and the testing data. You use the data to train the model. So, and that's why you see this going into this, okay? So you use the data to build the model, to build the model. And that's what, when we say build the model, we mean train the model, the data, train the model with the data. So that when you do the training, that produces a model for you. Now, what you are not done, what do you do with the model? You have to validate the model. First of all, come up with an accuracy. Like an accuracy is just a metric, something to check the performance of that model, something to check how well the model is performing. So you come up with an accuracy. How accurate is this model? And so after you've training, you check the performance of the model by using a metric called accuracy. There are other metrics which you will see later. And then to now validate, you now test the model on a different data called the test data to be sure the accuracy you are getting after building the model is good, because the model by default will perform better on the data that we use to build it, on the training data. Remember, we use training data to build the model. So the model has been exposed to it. It understands that I was built by this data. So by default, it will naturally perform well. But to now go further to validate that, oh, this performance is actually reliable, we now test it on a different data called the test data. And if that also performs well, that means your model is good enough. I will come back to this question here, that what happens when our model performs better on the training data, but worse on the test? Remember, test data is the new data that we want to use to validate, to ascertain the performance we are seeing from the training. So we'll come to that, oh, what happens? What do we call that scenario and how do we undo that? That's all we're going to be doing all this period of machine learning. Any question before we go into our lab Jupyter notebook to see how to do some of these things we have talked about? Any question?
Yes, I have.
Please go ahead.
Okay, in the slide, you said split data set into training and test.
Yes.
Okay, I'm a bit confused. I have one data set.
Okay.
How do I know which one I'm going to use for training, and how do I know which one I'm going to use for test?
Okay, that's a good question. So that's what we'll do. This thing is done randomly. Like, remember the question is, why do you want to split? We talked about why you want to split. Why do you want to split into training and testing? Why not use the entire data to build the model? Why?
You said to help in checking the accuracy.
Good. I said the essence of building a model is because you want to use that model in the future on a new data. But you need to simulate the experience to know how the model will behave on that. That's why we want to see okay, this is the data I have, but the end goal is to use this model in the future on a new data that I don't know. Even right now, I don't even know the data. But I know that the data in the future will be similar to the one I have here. So remember, it will be similar to it. Okay, so let me divide the present data I have into two parts. One part I will use to build it and check the performance, and the other part I will use to validate the performance I'm seeing on that training. How to do this, you will see when we go into our lab now. Okay. So okay. How to do that, you will see. But it's going to be done randomly. We will just choose. All we need is what percentage of my data do I want to use to build? That's all we know. We want to know. And what percentage of my data will I use to test? I can use like 75% of that data. Most times, the training data must be very, very larger compared to the test because we want to build it. So you need enough data to build. Testing is just to validate, so you don't need so much data. Okay, so we can use 75% of our data or 80% or 70%, depending on how large your data is, to build the model, and the remaining 25% or the remaining 20% or the remaining 30% to test. Does it make sense?
It does.
Okay. All right. So let's, without in the absence of any question, let's look at how to. Let's go to our Jupyter notebook. Sorry. I'm sorry. Oh, maybe I close it. Sorry. Okay, I thought I've opened it before, so let's see. So I have this intro to machine. Okay, so some of these I've explained. Can you see my screen?
Yeah.
Awesome.
Yes, sir.
So some of these I've explained in the notes, I've explained actually in the PowerPoint. So I will skip this first stuff. I'll still come back to regression, all of that, but I will use the PowerPoint. All of these, we'll be taking it one by one. Let me skip all of this before now. We'll come back to them when we're doing regression. So let's get up to the point we have that, we have a data and we want to do the splitting, and then we move from there. So I want to use a particular package called the Maglen. It's not really, we don't need it for so much. I just want to use the data inside. If you are using your own data, like the Titanic data, you may not need this package, but you can also do it because you can also install it, because we're going to be using more than the data inside later. We can use it for visualization. It's good for, I mean, it has a lot of stuff. So it's a small package and has some small data inside. So for just explanation, I will use some small data inside. So if you have not installed it, you can uncomment this thing in your notebook. So this is how to install a package. This is the name of the package called Maglen. Okay, so to install it in your Jupyter Notebook, you use pip install, and then you mention the name of the package. Suppose I want to do Panda, I'll do pip install pandas, pip install TensorFlow, things like that. So you can install it, run it. I have done that. So because if you don't install it, you cannot import it. So you have to run this before you can run the next cell. Okay, so I'll comment it because I have. So I'm going to import that package. And from the package, I want to use a very small data set inside of it called MakeWave. So I do from the package Maglen and the data set inside. So from Maglen.dataset, dataset is a module inside this package Maglen. From the dataset, import this dataset called MakeWave. Anything that starts with make inside this package means a small dataset that was manually made. So it's not a real world data. It was manually made to test those algorithms that we're going to be using later. So import MakeWave is a small data set inside the dataset module in package called Maglen. So after you've imported the data set, we want to call the data set. So we call this data set, and there is a feature inside called number of samples. For instance, by default, if I don't use it, if I just call MakeWave, now the way this data set is, the data set was divided into two parts. The part called the features, remember the features, those are our rows, those are the variables in the data, and the data set was divided into the features and the target that I talked about. Y here represent the output, example of the output you are expecting. Don't worry, we'll use our custom data set so you understand it very well. So if the goal is to predict whether it is cancer or not, maybe we have a column in our data called cancer. So each row there will either be, it could be 0 or 1, where 0 means no cancer, 1 means cancer. Each row represents a person, is an observation, a record about a person. But the column cancer will be standing for 0, 1, where 0 means the person has cancer, 1 means the person doesn't have. So that's an example. So that's what Y represents, the target, the output. The X represent the features, like maybe the weight of the person, that's one feature, that's one column. The weight of the person, the temperature of the person, all of that together is what stands as our X. Those are our features. Okay, we will see. I will explain this concept again when we use our own data. So let's run this. Now it has run. I can check my X. If I check the shape of my X and the shape of my Y. Remember, shape is used for dimension. You can see this by default. The number of samples I got here is just 100 rows, 100 rows, yeah. And meaning that, and then you can see it has one column. Just this is very small data. It only has one variable, one feature. But we know in most data sets you have many features. Even in Titanic, you have many columns, many features. But here is just a small data, okay? I can change it, this number of columns, you can see. I can change it to, let's say I want, instead of 100, I want 1,000. So if I run it, if I check the shape again, now is now 1,000 rows. So it's a small data inside the package. If you're not using the package, if you have your own data, you do not need to import the package. Remember, I'm only importing it because I want to use the data inside called make wave. So so this is just example. And I want to show you, now we have a data. We've been able to separate our variables from the output, the target, which is the Y. How do we split? How do we split into training and test data? This will answer Mr. Aloze's question. How do we do it? Now, we're going to be using, the package I'm going to use right now is the one that is the standard for machine learning, and that's the one we'll be using most. It is called the scikit-learn. It comes pre-installed with your Anaconda, okay? It comes pre-installed with it. You just need to import it, okay? So it's called the scikit-learn. That's the standard library to build machine learning model. That's what you even use in the industry and everywhere, okay? So we call it the scikit-learn. So in that scikit-learn is a big package that has many things depending on what you want to do. It has a part to load different models like linear regression, logistics, and some other model we're going to be building. And so there's also a function in this scikit-learn that can help us to split the data into training and testing. So we'll do from sklearn, which stands for scikit-learn, and the train test split is in what we call the model selection. If I press tab, you can see is in the model selection module. From scikit-learn model selection, import. Let's press tab to see many things there. There are so many things there. I need something to split my train test split. So there's something called train test split. So this function will help to split the data into the training and into the testing set. And it does that randomly. It randomly chooses some, based on the percentage we supply, it randomly chooses rows from the data as training and from the data as testing. So let's quickly show you how to do that before I allow questions. So this function will return 4 outputs. The features, we are going to supply the features, our X, and the output, our Y. So it's going to split the features into train. Suppose we name it S train, and it also split it into test, the part that will be used to test. That's for the features. It will also return the part of the target that will be used to train, and the part of the target that will be used to test. These are the outputs. So let's call the function train test split. So this function takes, the first thing it takes is the features that will be splitted into X train and X test. Then the next thing it takes is the target that will be split into Y train and Y test. And then the next thing, which is optional, you can supply the percentage you want it to use to split into train and test. By default, it's going to split into 75% to train, 25% to test. But if you can override that, so let me first use the default. And then we need to supply an argument called random state as a seed, because this function splits randomly. If you don't set a seed is used there for reproducibility, so that every time I come and run this cell, it's going to give me the exact same data that it actually split before. If I don't put that there, it will still run, but every time I run it, it's going to be giving me different set of rows. And that's not good enough, because if I've already built the model with this particular data and I do not set the seed, if I run it again, it's going to give me different set of rows to build as my training and test. If I now run my model, that means I'm rebuilding the model with a new set of data. And if you keep doing that, your model is building separately every time you are running this. So we normally set the seed to get the same type of data every time we run it. So if I do this, let me run this. Then I can, let me check the dimension. Remember the dimension was 1000 before. Let's check the shape now of the train and the test. I know this is a lot for you to take in. So you can see by default it uses 75%. 75% of 1000 is 750. So now we have 750 rows to train and 250 rows to test. Any question, please? Hello?
None from my side, even though I'm yet to grasp it.
You are here to understand it. Okay, Mr. Emmanuel, any question, please?
Sir, I must say that you are a great teacher, sir. I understand everything. Everything.
Okay. Thank you. Mr. Balaji, are you there? Any question, please?
Yes, I'm here, sir. I'm getting it.
Okay. Okay.
But sir,
Okay.
one question I have, which is how do you get the data for that make-way?
How do I
get the data for the make-way?
Yes, so it is not from me. It came pre-installed with this package, Maglen. That's why I say, because I need the data, I have to install this package. The package is called Maglen. So after installing it, to use it, I have to import it. And then the package has a module called data set. There are other types. For instance, if I do this and put comma and press tab, look at all the data inside. We have one called load boosting. Is the boosting data set about housing price. You have city bike, extended boosting, so many. So we have some on load, we have some on make. All the ones that start with make are the ones that were manually built. The load boosting, all those ones, they are real world data. But all the one called make underscore forge, make underscore wave, they are manually made by the person that created the package. So I'm just using the make wave here. You can see make wave. I was just using you can use any other one. So, but the way the data was designed, it was designed so that the creator, the person who made it, already separated the features from the target. Remember, the target is the example of the output that we want. Remember what I was talking about when I was talking about supervised learning, that it has an output, an example of a target to teach the model. So the person who made this data already separated them. Your data will not always come like that. So we will use an example of our own data, but we have to separate it ourselves. But this person has already separated them into features, which are the columns in our data, and target, or a single column, which is the example of the output we want to build. So the person already do that. That's why we supplied X and Y, meaning X should carry all of the columns, the features, the variables in the data, and Y should carry the example of the output that we want the model to predict. That's why we supplied, because I already know the nature. That's how all of the data sets that come pre-installed, whether in Maglen or the scikit-learn, that's how the creator already, they've made them to be in two aspects to make the journey stress-free. But data in the real world will not come like that. So that's why we use an example of our own data when we come to regression. So I expect you to, in your Canvas dashboard, I expect that you have something called reg data. It's a zip folder. I expect you to download it. You have this housing data there, and another data. So download it, extract it. So we'll see an example of how to use our own data. But I just started by using the pre-installed data. Does it make sense, sir?
Yes, sir. Yes.
Okay, so that's how, so we've been able to come to the point of how to split the data. Do we all understand that? Mr. Aloze, do you get it better now?
Yes.
Okay, good. So let's look at another, let's go back to our PowerPoint and look at what next. So we want to now start. So I will quickly introduce you to another concept. So this was where we stopped. So we've been able to see now, we have a data, which could be, in this case, I use the pre-installed, but remember in the real world, which we're also going to try, we have our data. Suppose we have access to the company data. Now we were able to split it into training and testing. So at this point now, I know that I assume that if you have a company data, you can split it into training and testing using train test split function in scikit-learn, right? Let's assume that based on what we just did, right?
Yeah.
Good. Now the next thing, the next thing is build. Okay, now I have my training data. How can remember the next step is to build the model, which we said train the model. So we train it, and then when we train it, our training means run the algorithms that we want to use on the training data. And when you run the algorithm on the training data, it's going to produce a model. Remember, that model means rules or functions or pattern in the data. It means rules that the model will now that will now be used on new data to make prediction. So that model is just like a function. I will show you when we get to regression. It's just a function. When with f of x equals to y, f of x, y equals to mx plus c. The y is the function. It's just a function that will be that's what we call model. That's a function, a rule. Okay. So how do we do the training? We'll see that. But remember, we build the model by training it, and then we check how well the model is performing by using a metric called accuracy, and then we finally test it to be sure that model perform well on a new data called the test data. That's the end goal. Even though we have a question at the left hand side here to answer that what happens if our model perform better on training, but we'll get there. So that will lead me. That will lead me. I'm going to skip this part. I'll come back to it because this is an answer to that question. But let me skip to a type of a model, because we said we are supposed to build a model we are supposed to build a model on the training data. What are the type of model that you can build? This leads me to the first aspect of the supervised learning. Remember, I said supervised learning is divided into two. Do we remember? What are the two types?
Regression and classification.
God bless you. Regression and classification. So I'll quickly fast forward to that point. By regression, do you remember? Okay, well, I'll put it here. Regression means you want to predict numeric outcome. Like I put the weather forecasting, predicting the housing price. You want to predict the sales of a particular product. That's what we call regression. The end goal is to predict a numeric outcome, numbers. That's the end goal. Okay? Classification means the end goal is to predict categories, that something, whether or not, whether a person has cancer or not, whether whether a customer will leave, we churn, we leave the company, we stop buying our product. That's customer churn prediction. Whether a customer we go and we move to the side of our competitors, things like that. That's classification. You are predicting categories where 0 can mean the customer will not leave, and 1 can mean the customer will leave, depending on how you encode it. But let's focus on regression. So regression can be divided into two. A little bit of statistics here. I won't go deep. We have the simple regression. We have the multiple linear regression. Simple linear regression and multiple linear regression. By simple, we mean you only have one variable. One variable, like the feature, just one. Like you want to predict housing price just using the population of that location. So the population is the variable, is the feature. Why? Our Y will be the housing price. Like in this case, we want to predict the sales of a YouTube, of the YouTube maybe videos. Yeah. So the YouTube videos is the feature, is the single variable. What we want to predict is the sales. And you know, sales are numbers. So that's a regression problem. Are we together, please?
Yeah.
Good. So all the dot you are seeing here, those are the numbers of views. Those are the views, you know, the views, the number of people who view the video of the YouTube video. Okay, so those are the observations in the data. The sales is the line that we are predicting. This blue line that you see here, that's the sales. That's the sales. That's what we are predicting. Okay? That's what we are predicting is the line. In statistics, they call it line of best fit, even though they don't explain what it means by line of best fit, but we'll break it down here. Best fit there means that our best assumption, our best guess of the sales of this YouTube. How the model, it is the model that comes up with these sales. Remember, that's what we are predicting with this assumption. How the model is coming up with it, we will see it when we want to code. And what is guiding it. So this is simple linear, but in most cases, in the real world, you will never have a single variable. We have many variables, like we saw in Titanic data and housing price. So instead of using the population alone, we could also use another feature, like in addition to the population, excuse me, we have maybe the income level of the people there, the number of bedrooms of that house, maybe the apart from the number of bedrooms, how many rooms in total are there, the space, the latitude and the longitude of that location or things like that. So those become other features. Okay. But for visualization's sake, that's why I'm using one variable or one feature and the outcome. Okay. Now, remember the blue line is the prediction from our model. But that prediction will not always be 100% correct. Remember the ... those are the actual observations. Those are the normal, the output, the original output, the original sales that we have in the data. And we are trying to build this model to make a prediction on this data to give us an example of the housing price when we give it a new data. And it's supplying us with this line. Now, the difference between the actual housing price we have and what our model is predicting is what we call the error. Obviously, that's the mistake our model is making. That's the difference between what the model is predicting and the actual output. And that's what we are trying to catch by the metric I told you about as accuracy. We are trying to determine how the performance of the model, what is the amount of error this model is making? What is the amount of mistake the model is making? By mistake, we mean what is the difference between remember we already have an example of the output. Now, our model is also now making a prediction that, okay, by my own rule, this is what I think the housing price should be. But we already have an example of the output. Now, comparing what the model is now predicting and the example we already have, which we call our teacher, our guide, the difference between that is what we call the error. And that's what we call the accuracy there. How accurately this model is performing. Any question on this before we move back to our Jupyter notebook? Do we get it? Hello, are you there? Hello.
We didn't get that last part.
Don't worry, you get it here now. Just hold those thoughts in mind. Or do you have a question? Please, let's talk.
No.
Okay, good. All right. So let's see how to do our linear regression here. Remember, I just explained. So let me go back and then move to linear models, which is the regression I was talking about. Linear regression is under a group called linear models. Now that line, this line we are seeing, that's still what I brought here. You can say, and it can be represented by this equation here. Now, what you see at the right-hand side, you see W, you see X, W0, X0, W1, X1, up to WPXP. What that means is, now all the X you are seeing here, those are the variables. Those are the variables in the model. Okay, those are the features in the model. The Y hat here represent prediction. The hat there means that's our predicted output. If it is ordinary Y, that's the actual one we have. But remember, the goal of this model is to predict something. So what we are predicting is the Y hat here. Okay, that's what we are predicting. So this is prediction. Okay, that's prediction. We stand for P. Okay. Now all of these ones here, all of these, that's the that's what we are using to predict. But the main thing that we know are these X's, this X. Those are the variables in the data. Those are the features in the data. Now the W is the main goal of this model. The model is the W's are the coefficients. In neural networks and deep learning, they call them weights, but let's use them as coefficients here. Those coefficients, we don't know it. We only know we have data, which stands for the X. We know the number of people that live in that country, that place, the population. We know the income of each person. We know let's say we have access to that. We know the number of bedrooms. Those are the X's that we know. We know the number of rooms. We know how many bathrooms are there, how many rooms, how many bedrooms. We know all of those ones. Those are the X's that we know. So the goal of this model that we want to build, the goal is to come up with the appropriate values for this coefficient, these W's, that will help the model to make a good prediction. So the rules that I talked about before are the rules to help the model to come up with the appropriate coefficients, the W's here, that after multiplying them with the input, with the X's that we know, it will help to generate the correct price of a house. I don't know if this is making sense. Is it too big is it too much? Are we getting it little by little?
Exactly. Little by little.
Yeah,
is
little
fine.
by, don't worry, it's pieces, but you get it there. You get there. Okay. So remember, the goal of this linear model or linear regression, which is an example of linear model, is to come. We know the X's. We have access to that one. That's the data we have. But we don't know the weight, the W, the coefficient. That's the goal of the model. That's what the function we say we want, which is the model, is trying to come up with rules to generate the accurate coefficient for each of the inputs, each of the variable we have in the data, that will help you to predict the accurate price of the house. So the initial time we supply the input, those features, those number of bedroom, number of rooms, number of, the long term, like when we supply all the X's to the model, the very first time, the model will randomly come up with coefficients. We do that the first time, come up with random. I'm showing you what is going on inside the model. The first time is going to come up with randomly, just say, oh, I think the coefficient for number of bedroom maybe is 0.5, the one for this is this, the one for that is this. Trying to find which model, which of those variables is actually very, 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 very important to come up with the accurate price. So it's going to randomly generate those coefficients by itself. But obviously that random values at the very first time they will be inaccurate. So, and then it will use it to build a model. Inside it, what goes on there, it makes a prediction inside before the one you saw. And then compare that prediction with the example that we have. Remember, we have an example target, which is an example of the housing price that we supply. That's the Y that we supply there. That's the Y that we got. So it's going to compare what it predicted with that example Y and saw that, oh, my prediction was very, very far. Then it will now correct it, adjust these W's again. It will adjust it. That's all what neural networks people are shouting about is about. For those of you who go higher, who get to that, who do that. But I'm just explaining what is going on here. So it's going to now, after comparing them, it's going to try to adjust the W's, the coefficient, the weight, and then do it again. Then it will become better. It adjusts it again, those W's, and do the product. Remember, there is a product going on, multiplication going on here, because each X has a weight, has a coefficient. Okay, so it does this over and over and get the accurate output. The unfortunate thing is that for simple machine learning models like this, it does all of what I said one time. And neural network does it multiple times and come with a better result. That's why, for those of you who have heard of neural networks, deep learning, that's all it's doing. It's the same thing here, but in an advanced way. But let's not go into deep into. So all of that, is all of what I've just explained is what is going on inside this model here. Before I come out with this line, it has done most of what I explained. Okay, so let's look at what I explained, how to come up, everything I explained can be done in like 2 or 3 lines of code. So the code is not what is important most in this point, but the understanding of what you are doing when you are writing the code, because that will help you to be able to explain to a non-expert. That's why I'm taking more time in this aspect. Okay, we can do all of those things in 2 lines and you will see that. Okay, so what we need, remember, we need the model, the regression model, right? Because the data we have is a regression output. We can, if you want to see it, you can actually check it to see, let's see what is inside our X string. At least let's see the first 5 or the first 10. You can see they are all numeric stuff. And if you want to check your Y too, you can check, let's say, the first 10. You can see example of the targets. You can see that the targets they are not categories, they are numeric numbers. If they are categories, then the problem will be a classification problem. Are we getting it? Are we getting it? So this is why we say it's a regression problem. You can see the output. If they are 0, 1, 0, 1, 2, all of those things, we know it's classification because those will be category, but these are numeric. So remember, this is the Y. So that shows you we're dealing with a regression problem. Okay, so we want to build the model. The first thing, we import the model. What kind of model we want to use? Here we want to start with linear regression. There are other models we'll see. So you do from scikit-learn. Scikit-learn has a module called linear module. Okay, so if you don't know, after you put dot, just press tab. So many things there. You can see from scikit-learn data set. It has some data set. 2 example will come to all of, I don't know if we get there, that's a different type of model. But we see linear regression here from scikit-learn linear model. Import, there are models inside the linear model. We have, you can see all of this on ARD regression. We have the elastic net. We have many Uber regressor and all of that. We have lasso. We'll get to lasso maybe tomorrow. So, but we need linear regression. So once you import that, so at this point, it is an algorithm. That's what we call algorithm. There is a difference between algorithm and a model. An algorithm is it is an algorithm because you've not trained it on a data. After you've trained it on a data, it is no longer an algorithm. It is now a model because it would have come up with a function that will be used to make prediction. But right now it's an algorithm, linear regression algorithm. So it is a class. We didn't touch classes in Python. Yeah. But so first thing you do, create an instance of the class or instantiate it. Let me call it LR. Okay. Then I'll call the linear regression. So the first thing, import it. The second thing, create an instance of it. LR equals to linear regression. So this, what we call fit, is what we call training. When we say fit the model, it means train the model, meaning supply data to the algorithm. And then it will come up with a model. Okay, so we do LR, which is the instance of the linear regression. Then we do dot, press tab, you see fit, dot fit. And what do you supply to the dot fit? Supply the training data, which is the X train and Y train. Those are the training data. Remember, we split the data here into X train, Y train, X test, Y test. X carries the features, Y carries the target, the output, example of the output. Remember, this is a supervised learning. And then if we want to test it, we use X test and Y test. So because we are still at the building state, we supply the X train and Y train. So this single line will train the model. That's all. This single line will train the model. If we want to get example of the weights, these W's that I talk about, the W's are the weights or the coefficients. The B is the intercept. It's still part of what the model is trying to come up with. So if we want to do that, remember this particular data has a single variable. So, and I said each variable, the model will come up with a weight or a coefficient for each variable. So when you have a single variable, how many coefficients will the model come up with? I'm not sure you guys are following me. Are you?
Sir, you said what?
Please repeat your question.
Remember I said the model will come up with a weight for each variable. That's why you are seeing W beside every X. The X are the variables. The model is trying to come up with the right weight or right coefficient for each variable. So when in our case where we have a single variable, as you can see here, 1, how many coefficient will the model come up with?
1.
1, because it come up with coefficient for each variable. So if you have one variable, it will only come up with 1 coefficient. So now this line has already trained the model. We can check the coefficient that the model come up with by using, we can do print. You don't have to do print. Just call up the class, which is the LR, that's the linear regression that we just trained. Dot, press tab, you see coef. This means the coefficient. So if you run this, see, the model come up with this prediction that this weight has 44.59, 0.4459 coefficient. That's not the accuracy, that's the weight, the coefficient. The W I showed you up there. Remember, the goal of the model is to come up with the appropriate coefficient, because the more appropriate the coefficient, the more the model will perform very well. Let's check the performance of the model on both the training and the testing. Remember the performance, I told you, we are using a metric called accuracy to check the error the model is making, the mistake is making. So let's do print. Let me fine tune it very well. Train accuracy, you don't need this one. I just want to make it more readable. Okay, then I give it a space. I give it empty curly bracket. That's where I want you to put the answer. You don't need all of this. The main thing you need, I'll show you now. Because I put empty curly bracket, I want you to format the result. So the main thing you need now is what I want to put in this bracket. So you do, you call on the model you build, which is LR. It has a score function. This score is trying to score your model to come up with the accuracy. So let's do it on the X train, the training data, and Y train. If you don't need all of these, this thing I wrote, all you need to do is just to do maybe print, and then you supply the name of the model, LR dot score, and then you supply the train, S train and Y train. That's all you need. All of these ones, train, accuracy, put the answer inside this format, is just to beautify it. The main thing you need start from LR.score in bracket X train, comma Y train. So let me copy this and do that for testing too, to see how it performs on the test data. Remember, the test data is the new data, standing for an example of future new data, future data that we will supply to the model. So let me change this. Instead of train, we put it as test. And instead of X train, we supply X test. Instead of Y train, we supply Y test. If I wanted to make it to 4 decimal place, I'll put colon dot, put 4F, meaning up to 4 fractions, 4 fractional, stuff. So if I do that, see, the model is giving me a training accuracy of 61.25, or you can convert it to percentage, approximately 61% out of 100. And on the new data, it's giving me 63 point maybe 8% or 7%. So that's the performance of our model, meaning the model is making about 38 or 39% mistake on the data, on the training data. I don't know if what I've said so far makes sense or any question. Please ask question, please.
It makes sense, but one question I wanted to ask, maybe I'll just have to hold on to get to that point. So you just made a comment that the data is making about 39% mistake. How do we correct such a situation?
Okay, that's a good question. But before that, any question, Mr. Balaji, Mr. Emmanuel?
No question for my side.
Okay, Mr. Balaji, are you there?
Yes, sir.
Are you? Do you get it up to this point?
Yes, but the question I want to ask is that the training accuracy. Okay, can we test for the both instead of using this testing and accuracy or something? We said we can use just only LR.score for us to test, and it will work too for the testing accuracy too as well.
If I want it on only testing, then I will just supply this one, LR.score, and pass in my testing set, which is X test and Y test. That's all. I want to check it on both, and I will show you why you need to be checking on both very soon. I want to check it on both. That's why I did it for both. Okay?
Okay, sir.
Yes. So Mr. Alozie asked a question that, sorry, can you ask your question again? Okay, how do you correct the mistake, right?
Yes.
Okay, before you even know, ask on mistakes or not. Is this performance, is it okay? Is it the best? 61%.
I will say it's not.
why my reason being the margin is high. At least I will expect something of 0.7, 0.8 on the training accuracy. Then maybe on the test, maybe 0.81 if the training accuracy is 0.8.
Okay, good. Okay, let's even try to explain this to a non-expert. Oh, we've just come up with a model and we say, oh, this is the accuracy. You know, we know what accuracy means. The layman doesn't know. The business manager doesn't know what you mean by train accuracy or test accuracy. What this means, let me explain it. It means that if you said our train accuracy is 61.2 or 61%, we are saying that on average, our model, this model will correctly come up. Let's say this is for housing price. We correctly predict the price of a house with 61% of the time. And the remaining 39% of the time, the prediction will be wrong. So we always want a good high accuracy. We don't want our model to make much mistake, but emphasis should be on the test, because the model will generally perform well on the data that is used to train it. But on a new data it hasn't seen before, in this case, the test data, we want the accuracy to be high. So that's why we are comparing it. That's why I had to check it on the test. We need to be comparing these two, and we will put more emphasis on the test. Okay? Now, I would say for this data, a data having only one variable, the model did very well, because the more the features in the data, the more information you are supplying to the model. But this model only have access to one feature, maybe just the number of population. And it came up with a model that will predict the price of the house 61% of the time, but 63%. Then this model did very well. If we supply many variables and it still gave us then we know the model is not doing well. Do you get the idea of what I just said?
Yeah.
Okay, good. But so let's assume. So now let me show this. Can you see my slides?
Yeah.
Yes, sir.
Okay, good. Now remember, maybe I did. Oh, okay, good. I put a question here. Okay, I think it was here. Yeah, so there was a place I put a question. Okay, what happens when our model performs better on the training data but worse on the test data? In our case, did we have that? Did the model perform better on the train than test?
No, it's better than test than the train.
So that will lead us, what we'll tackle tomorrow. A concept called, okay, I think I even put it here, a concept called overfitting, underfitting, and generalization. So let me explain this so that we will deal with it more tomorrow. What we call overfitting means the model performed very well on the training data, the data that we use to build it, but worse on the test. And remember, our focus is on the test. So that means our model overfit the training data. By overfitting means that our model memorizes all of the patterns, including the noise in the data, and it was too weak to perform very well when we gave it a new data it hasn't seen before. And look at it on the right hand side. It's trying to cram to make sure it perfectly match all of the red. It's memorizing all of the observations, all of the patterns. But the unfortunate thing is that it memorizes the noise too. The noise are things that are not needed in the data. It did. And then such model will give very high accuracy on the training. So if you don't check it on the test, you will think your model is doing very well. That's why we normally check the performance on the testing data too, to know whether this model is just simply overfitting, meaning just simply memorizing the patterns, including the noise in the training data, but too weak to do very well, to perform very well on the test data. So that's overfitting. Underfitting is when the model is too weak on both the training and testing. It's too weak to perform very well on the training set. So that model is too simple to understand the pattern in the data. So the accuracy on the training is very low. And obviously, because the accuracy on the training, the what you built is low, it will surely be low too on the test. So underfitting, low accuracy on training, low accuracy on testing, meaning the model is too simple to understand the pattern, the pattern in the training, and as a result of that, it gave low accuracy on training and definitely low accuracy on testing data too. The good compromise is what we call generalization, meaning your model generalizes well. That means your model performs very well on the training and much more on the testing. An example of it is our model here. It performed well on the training. Remember, my well here is because we're using a single variable. So we say this model gave 61% on training and much more on the testing, 63%. So this kind of model, we say it generalizes well. That means perform well on training and testing. Can someone summarize the three? Overfitting, underfitting, and generalization. What we just said. Who want to try?
Yes, sir.
Okay.
To ask the question. Are you saying that once the training figure is there's no let me say the training figure and also the testing figure has just little whether little or small differences, that means it is being generalized. Or if the training figure is lower than the testing figure, which means it is unfitting, it's underfitting. And why if the testing figure is higher than the training figure, which means overfitting. What you are,
Okay, who can correct Mr. Bolaji here? Who can, I'm not correct, who can answer this question? Who want to try? Mr. Emmanuel, are you there?
Sir, I did not hear him properly. I didn't.
Okay, do you want to explain? Do you want to explain these three concepts in summary? What I just explained.
Yes.
Okay, go ahead.
For overfitting, the model performed very well in the trained data.
Okay.
But performed badly in the test data.
Okay.
For underfitting, the model, the model did not perform well in both the trained and the test data. Why for generalization, it's performed for both the trained and the test data.
And much more on the test, right?
Yes, much more.
So that answers your question, Mr. Bolaji. However, the margin is subjective. So if the difference between the training accuracy and test is very large, meaning it performs very well on the training and worse on the test, meaning the margin is large, you say it's overfit. Okay, are you there, Mr. Bolaji?
Yes.
So, but it's subjective, it's based on you, but with time you will get to understand that, but most time the margin is high. And underfitting, obviously both are very low. Like a normal data, a normal model, if you have large data and the model is giving you 60% on both training and testing, that's underfitting. You want, most time, you want your model to be very accurate. You can imagine that this model is about life, is on health. You want to predict whether someone has a cancer or not. If your model is giving 60%, that means most time, people who have no cancer, you would predict that they have cancer. And people who do not have cancer, you predict that they don't. People who do not, who actually have, you predict that they don't have. And remember, someone has cancer, you predict that they don't have. That can lead to death, right? That the person can die now because the person can go and be living as if he doesn't have. Meanwhile, he has. So you want your model to be very, very high, such that the mistake is so small that it will, in most time the accuracy will be very, if you can get 99%, in fact, that will be the best. But you want it, because you are building the model for future, you are focusing on test, because test data means the model hasn't seen that data before. So we put more emphasis on the testing, because that's the test data is an example of the future data that will be similar to the data we used to build it. I don't know if it makes sense. And if that model has that, we say the model generalizes well. Okay? Hello?
I want to ask a question.
Go ahead, sir.
Back to splitting the train data and the test data into 75% and 25%.
Mm-hmm.
I don't know how, assuming I have production data from a producing well,
Okay.
and I have pressure information from
Mm-hmm.
a producing well, and I have the oil production
Mm-hmm.
from a producing well, which I want to see how, in petroleum engineering, it's called forecasting, how the performance of the reservoir
Mm-hmm.
with the pressure and how the oil production will be in future.
Mm-hmm.
And then I put in the data into I load the data, then it divides it into training
Mm-hmm.
and test.
Mm-hmm.
How will it predict the
Okay.
How will it, I don't know how to put it now, because my question is, how does he use, because it's still the same data, so where is he getting the test from? It's still the same data, I just split it into 75 and 25.
Yeah, okay, this is sir. Okay, look at this picture. So the test is also part of the data. You can see the line here.
I know.
So it's still part of it. Like, I'm going to use, because it's a future stuff, we want to simulate the future in the present. That's what we are doing. We want to show how this model will behave in the future with a new data that we collect in the future. The future can be a day, 2 days time, 1 week's time, remember? So we want to simulate how this model will perform if we give it a new data. And that's why we need something to check it now. You can't just come and tell me as a data scientist that, oh, I built a correct model. This model, if you give a new data, it's going to give you 100%. I'll tell you, show me how you know that. So how to show me how you know that is why the data scientist is coming up part of this data as a test data, because it's going to block the model from seeing this test data, because the test data is not going to be used for training, for building the model. So the model has never seen the test data before. So that's an example of a future data. I don't know
I do get you, but what if the dates, will it like data that has dates?
Okay, that becomes a time series problem. So that's a different problem now.
Okay, no problem.
That's a time.
Maybe with time I will get to understand it. But
so that's a time series problem, and there's a way we handle time series problem. For time series problem, If we want to split the data, we will not do it randomly. Yes, but that's a different thing.
Because why I'm saying it, the data I use has to do with dates.
Yeah, but it doesn't really mean if the same feature, the same variable that you have in your current data, you are so sure that the future data will also have the same variable. You are so sure that the condition will be the same.
That's an assumption, but the condition will never be the same.
So on what condition are you referring to?
That's why I use the word pressure and oil production.
But those ones are variables, right?
Yes.
No, so by that condition, I don't mean variables.
Okay, what condition do you mean?
So let's focus on the variables. Condition mean that, maybe we're not considering the time. We're assuming that the time, the pressure, maybe the pressure has nothing to do with the time the data was collected. We want to assume those ones, they don't have effect, right?
Yeah.
Yeah, so if those are the conditions, we assume those ones. So those are the assumption we are making, that the pressure or the whatever those features, the pressure has nothing to do with the time you collect, that data. So we're assuming that the same variable that you have in the present data, let's say the pressure, maybe on another one, will also be in the future data. Then you can use it you can build your model. You can use it for future prediction, but the problem comes when the variables changes. You can't. Yeah.
Okay. So what he's trying to say is that pressure is what drives some of those changes in the variable. Because we're looking at pressure now. Changing with time.
A variable? Is it a variable?
Yes, it changes with time. It changes with time because as you are producing from the hydrocarbon, the pressure in the reservoir is actually changing. So to be able, like you said, time series, you said time series stuff, because as you're producing from the hydrocarbon in the subsurface, the pressure is changing with time, and it's also driving changes in some of the variables that are in the reservoir.
You are saying two things, Mr. Emmanuel. You are mentioning variable, you are mentioning pressure. I say, is pressure a variable? Remember, a variable means a feature.
Yeah, I think so. If you ask Mr. Aloze, is a petroleum, I think the pressure is a variable that changes with time.
No, wait. In my data, what are the columns in the data, Mr. So by those columns, I mean variables, features.
Okay, let me explain. Maybe we're not. I think we have. We're not understanding ourselves.
No. I want to be clear to answer your question.
Okay, now my variable is pressure and the hydrocarbon.
Okay, before
that's the oil.
Before I move on, and you are collecting values so our each row represent values for pressure
and value for oil.
Yes, and hydrocarbon.
And it's being collected on daily basis.
Fine.
So
wait. Before I want to be so that as we are good, let's focus on a particular day.
Okay. On a particular day
of data.
On a particular set of data or a particular day.
Let's say
I'll go and
day.
Okay. Like on a Saturday like this, I'll go and collect the pressure information and then the oil production information. You understand?
Yes.
But in real life, the production of oil is dependent on pressure, and pressure changes with time, because the more you produce the oil from the reservoir, the pressure tends to reduce.
Before you go ahead, so what is our target? What do we want to predict?
My question is, in such a situation.
Wait, before you ask your question, what will be the goal if you're building a model? Okay, what is the model going to predict?
Predict the performance of oil production.
So that's our Y. The
X
in this case, the X in this case will be the what? The
pressure.
Pressure and hydrocarbon.
No, the date. First, I normally use the X X should be the X should be the pressure and the oil production.
No, now
Then
I thought the oil production is what I want to predict, right?
the Y is the
We are taking
outcome, right?
You can. What do we want to predict?
I want to predict that in the future, how will the performance of the pressure and the oil will look like in the next 10 years?
So that's not what you are predicting, sir. What you want to predict is the production, right?
Yes.
That's our why. That's what you are predicting.
And
So,
then the pressure too. How will the pressure look like?
The pressure becomes the feature, the X.
No, I want the X to be the date, the time.
So now, if you are putting time as a consideration, that means you are saying the time has effect. The time the pressure is collected, the pressure of the oil is collected has effect on the production. So that becomes a time series a problem.
Okay, maybe when we get to that time series, I'll be able to ask this question.
Time series is out of this scope.
Okay.
Because it's a separate, if you want me to do a class on it, I can. It's a separate aspect. What I'm trying to get to is this. Let's assume the time has no effect. That means, that's why I say let's focus on a single day of data. So suppose that the time, we are making an assumption that the time the pressure of the oil is collected has no effect. Suppose that we want to see the effect of the pressure of the oil on the amount of production. Are you with me?
Okay, Kenny, let me give you a real life example, so that I hope I'm not taking much of the class time. I can forget about it.
No.
But why I'm asking this question is a kind of important, because definitely I'm going to handle such a situation whereby.
Do you have a data example of data?
I can generate it I can generate it and give it to you tomorrow.
So generate it and let's look at it in the lab tomorrow. Let's look
now
at it.
Or tomorrow.
Tomorrow now.
Okay, tomorrow I'll bring it and show you.
Because the class is almost ending.
Yes, yeah, I'll